Hi, I'm Matt Lenhard, and today I'm going to be talking you through tracking syscall and function latency in your Kubernetes cluster using eBPF alongside BCC tools. So in this talk, I'm going to walk you through really everything necessary to run this in your own cluster, as well as like an actual demo. So we're going to get started with installing BCC tools on your Kubernetes cluster. BCC tools is essentially just a framework for writing and running eBPF based programs. It has like this nice Python interface where you can pretty easily kind of like modify the existing tools or write your own tools even. And it's all in Python, so it's super easy to get started. Next, we're going to talk through how to correlate a pod to its underlying PIDs. This is so that we can attach the BCC program directly to those PIDs and give you a nice little interface so that you can just type in a pod's name and then automatically attach the BCC program to that PID. After that, I'm going to walk through the code examples, specifically for tracing the function calls and syscalls. We're going to be using trace points for the syscalls and USDTs for the function calls or user space calls in your application. Next, I'll do a demo in a Kubernetes cluster running the some of the code we've written along the way. And finally, we will wrap it up by talking through some of the overhead we've introduced with this instrumentation. As I'm sure everybody knows, collecting all of this data isn't free, and there's definitely some downsides to it. So I'll walk you through, what are some ways to kind of mitigate the overhead we're adding, as well as, how do you even track the additional overhead. I also set up a GitHub repo that you can use to follow along. It's got everything from the Kubernetes manifests to the actual kind of like code samples I'll be talking through. To get started, really, it's as easy as kubectl apply the manifest and then getting a shell into the given pod. That way that you can run any of the BCC tools or run the tool we're talking about specifically on one of your pods to get the track that function latency. Cool. So the first step is installing BCC tools. In order to do this, we're going to set up an init container, which you can see in that k8s YAML file in the repo. But what's happening is we're basically running this init container to grab the Linux headers that correspond to the kernel version you're running. From there, we'll move them into lib modules so that the tools will work as expected. In the base image, we're basically just building BCC from source. We're copying in that main.py file, which is going to do all of the tracing. Finally, we're setting up a bunch of volume mounts. The kind of two most important ones are the lib modules volume mount, which we need in order for the BCC program to run for the kernel headers, as well as we will be mounting the proc file system so that we can do that pod to PID correlation. You're also going to need to run the container as privileged, as well as add the sysadmin, and in some cases, depending on the tool, netadmin and systrace capabilities. So if you are using something like a Fargate or a GKE autopilot, unfortunately, most of the kind of like eBPF tooling isn't going to work because you can't run those privileged containers. With Fargate, you can't really run the daemon set. So unfortunately, you're going to either need like a vanilla k8s install or just GKE/EKS themselves. So how do we get the pods PID? The first step is we're going to be using the Go client to fetch the pods UID. We'll then loop through the proc file system, look for that mountinfo file, search for the UID within it, and finally we'll set up a informer to maintain state. This essentially is just functions you can add when pods are created, deleted, or updated. So getting a pod UID, pretty easy. Set up the in-cluster config. We'll use the core v1 pods get function call to grab the actual pod itself. We'll pass in the name and the namespace. From there, we have the UID. Next, we will loop over the proc file system like I mentioned. So in this example, I've mounted proc into the /host directory. We will loop through all of the PIDs within the proc file system, look into that mountinfo file. In there, we're going to look for that UID. If we find it, we know that that PID belongs to that pod. Finally, we're going to set up an informer. Just some example code here. There's obviously more to it, but basically anytime a pod is added, we can add the UID to like our storage system. Anytime it's deleted, we can remove it. This allows us to do is, anytime a pod is created, automatically attach our program to that corresponding PID. Cool. So this is the actual eBPF functionality, and at the heart of what we're doing is we're adding probes to the entry and exit functions in both the system called tracepoint and USDTs. So I'll start with the syscalls. And what you're looking at here is we're adding some functionality to the sysenter tracepoint. We're grabbing the PID. We are using that PID to create a map, and we'll use this alongside the exit call so that we can time how long that given system call took to execute. So yeah, as you can see, we're using BPF K time to get the nanoseconds, and then the last line here, we're adding all of this information to a BPF map. So yeah, the next step is hooking sysexit, where we're going to grab the current PID. We're going to use that to look up the syscall in the map, and then from there we can calculate how long that system call took to execute. Finally, we're going to delete that from our map. So tracking functions latency, specifically for like the user space language you're using, is a little bit different, but kind of uses the same sort of like paradigms or processes. We're going to be setting up a function trace entry that we're going to be adding to a USDT later on. So the heart of what we're doing is pretty similar though. Grab the PID, use BPF K time to start the timer. We're going to read the arguments from the trace point, specifically the class and method. This will differ based on the actual language you're tracing. So this is Python, but if you're using, Ruby, PHP, Java, whatever, it's going to be different. If you look at that main.py file, you're going to see kind of the differences between the languages. So yeah, you can use that to kind of substitute in what language you're using. But yes, we use that class and method alongside the PID, and we add it to a map so that we can, in the exit or return trace point, calculate how long it took to run, and also do a count so we can see how many times a specific function took to run. Again, the read arg is going to differ depending on the runtime, so just if you're copying this code out, make sure to check out main.py and update it for your language. Final step is to add these USDTs to the correct probes. So trace entry and trace return are the functions we kind of just walked through earlier, and the entry and return probe. They will differ depending on the language again, so you're going to want to check out that again, Python main.py, to figure out what works for your language. Awesome. So now let's jump into the demo. Cool. So this is, I've already set up a Kubernetes cluster here. The first step I'm going to do is get a shell into the daemon set that I've created. I've set up a program in here that will automatically look up the PID for a given pod. So it's that Go file in the GitHub repo. But yeah, you basically just pass in your pod's name alongside the namespace, which I know this one's in the default, and you have the PIDs. I'm going to be running this on a actual Python program I have running in this pod, but it should work pretty similar to any application or any pod that you're running. So I'm going to run that main.py file in the repo. And what we're going to do is we're going to pass in the PID. We're going to pass in the language, which in this case is Python. And then the other flags are L for latency and S to trace the syscalls. Next, we're going to let this run for a few seconds. This is basically like a program I have running on this node. One thing to note is that if you have multiple nodes in your cluster, you need to make sure that the pod and the daemon set that you're running this from are the same, or they're on the same node. So just something to kind of keep in mind when you're doing this. Cool, now that we've let it run for a little bit, we're gonna send a signal to exit it out. But yeah, what we're looking at here is the number of times a function was called and how long it took. And so you can kind of pretty quickly get an idea of what I kind of did here is function A calls function B, which sleeps for a while, which then calls function C. And so most of the overhead here is in function B. If you check out the in the repo, I've got that sample app folder, which has the actual code here, but I think it's pretty clear that it was, function B was causing all of those issues. And so, yeah, you can run this on, it's pretty easy to run this on any, application you've got running in production, and you can see, a real-time count of how many times a function is getting called, the actual latency of those functions. And so when you're seeing performance issues in real time, you can get a super easy insight into what might be causing it. So, like I said earlier, all of this insight comes at a cost. How exactly, do we keep track of it, and what are some, ways we can mitigate the additional overhead we've added? In order to make sure that you're keeping track of these stats, you want to use you can use the sysctl command to enable them, and then there's kind of the easiest way is using BPF tool, and there's kind of two core commands through BPF tool we can use. BPF tool program show, which I'm showing you the output of below. What you're going to want to look for there is the runtime and run count, and that'll get you a pretty good idea of your applications, kind of like the additional overhead you're adding from your BPF program. There's also BPF tool profile, which is going to give you a little bit deeper insight, so you can see the cycles, the instructions, and the L1 cache loads and misses. This specific program that I've walked you through, there's kind of like one glaring issue or one major hit you're going to take, and that's with the user space USDTs we're adding. So those are interrupting, or they're adding, running on every single function entry and exit, which, from that you can get some really cool information like the latency of every single function call, how many times each function ran. You could do things like build out stack traces. The issue is that it does add a lot of overhead. So one of the ways that we've found to mitigate this is by actually periodically detaching and attaching. So the additional overhead isn't actually in attaching it. What we've found is that it's, even if you attach and do absolutely nothing, you just continue, you're still going to see a lot of overhead. But if you attach, run it for some small period, maybe you built out a stack trace, or you do a count of a certain number of functions, and then return and detach the probe, the actual overhead isn't that much different than what you'd see in a stereotypical APM, or maybe like profiler. So something that we've kind of learned is always be tweaking, kind of figure out ways you can make improvements, but that's kind of like an easy win that you can add. So yeah, that kind of sums up my talk here. I hope you enjoyed listening to it. Had a lot of fun giving it. I'll be hanging out here to answer any questions you might have. I always love talking performance, kernel stuff, anything to do with eBPF. So if you just want to, reach out and talk more, my email's below, matt@contaiниq.com. Always looking to talk to other engineers who are passionate about this sort of stuff. Again, thanks again for watching, and